Hello, my dear students. This is U. Srinivas, Senior Chemistry Faculty from Gosala Campus, Vijayawada. Today, I am going to discuss about effect of temperature on rate of the reaction. Effect of temperature on rate of the reaction in chemical kinetics. My dear students, you know this, irrespective of nature of the reaction, whether it is exothermic or endothermic, rate of the reaction increase with increase in temperature due to increase in number of effective collisions. As effective collisions increases, as the number of effective collisions increases, rate of the reaction increases. Why? Because only effective collisions lead to the formation of the products, but not the all collisions. And for every 10 degree or 10 Kelvin rise in temperature, rate of the reaction become double. For every 10 degree or 10 Kelvin temperature, rate of the reaction doubled. The ratio of the two specific rates measured at a given temperature that differ by 10 is equal to either 2 or 3, and this ratio can be known as the temperature coefficient. This is called the temperature coefficient, denoted by the symbol mu. Mu is nothing but the temperature coefficient. What is the temperature coefficient? Temperature coefficient is the ratio between any two specific rates measured that differ by 10 degree or 10 Kelvin. 10 degree or 10 Kelvin. That is temperature coefficient, denoted by the symbol mu. And mu value lies between 2 and 3. Mu value lies between 2 and 3. Mu value lies between 2 and 3. From this we can say for every 10 degree or 10 Kelvin rise in temperature, the rate of the reaction become doubled or tripled. So what's the mu value? It lies between 2 and 3. Coming to effect of rate of the reaction on temperature. This is given by Arrhenius rate expression. The temperature dependence on the rate expression given by Arrhenius, which is K is equal to A into e power minus EA by RT. K is equal to A into e power minus EA by RT, where K is rate constant, also known as specific rate, also known as velocity constant. And this e power minus EA by RT denotes the fraction of effective collisions. Where A is Arrhenius factor or frequency factor or pre-exponential factor. Arrhenius factor or pre-exponential factor. Since it is preceding the exponential form, this is known as pre-exponential factor. Or we can say frequency factor, since it is given by Arrhenius, also known as Arrhenius factor. And this expression is Arrhenius expression. And here EA is nothing but activation energy. EA is activation energy. What is the activation energy? Activation energy is the minimum additional amount of energy required by the reactants to attain threshold energy. What is the activation energy? Minimum additional amount of energy required by the reactants to attain threshold energy is an activation energy. So I will explain how the activation energy would be by plotting a graph between the potential energy as well as the progress of the reaction. We can say reaction coordinate. This reaction coordinate is also known as progress of the reaction progress. Let us draw a graph for the exothermic reaction. Exothermic reaction. Since I mentioned this is the graph for the exothermic reaction, energy of the reactants dominates over that of the products. Reactants energy is more than that of the products. So that I should plot a graph like this. Energy of the reactants is more than that of the energy of the products. Say this is the energy of the reactants. Say this is the energy of the products. And this is an energy barrier. That energy barrier can be known as threshold energy, ET. E for the energy, T for the threshold. This energy barrier is threshold energy. Any reactant molecules, in order to form the products, must cross over this energy barrier. Then only products formation taking place. Reactant molecules shall have to cross over this energy barrier. Then only products formation taking place. The minimum energy required by the reactants to form the products called threshold energy. What is the threshold energy? Threshold energy is nothing but the ET. It is the minimum energy. It is the energy required by the reactants, to form the products. That is threshold energy. This is normal energy. Energy of the normal molecules. This is the required energy in order to form the products. And the difference between these two is an activation energy. The energy difference between threshold energy and energy of the normal molecules can be activation energy. That is activation energy. This is the activation energy for forward direction, because this is the direction indicates from the reactants to products. Similarly, if you want to write an activation energy for the backward, this will be the activation energy for the backward. Since this is the backward direction, I need to mention as A dash to distinguish, to differentiate. Since both are the activation energies, this is for the forward direction. Coming to from backward direction, this is activation energy of the backward direction. And the energy difference, activation energy difference between these two can be known as delta H of the reaction, enthalpy of the reaction, heat of the reaction. This is delta H, enthalpy of the reaction. Okay. So what is the activation energy? It is the minimum additional energy required to attain the threshold energy. Minimum additional energy required to attain threshold energy. So nothing but activation energy. So once again I am going to write the expression K is equal to A into e power minus EA by RT. Taking logarithms on both sides to get ln K is equal to ln A minus EA by RT, and this will become ln E to the base E. This ln E to the base E value is 1. Ln E to the base E value 1. So that can be ln K is equal to ln A minus EA by R into 1 by T. Comparing this equation with the straight line equation, y is equal to mx plus c. This is the y variable, ln K y variable, and this is the x variable, 1 by T is the x variable, and this will be m, and this is the c. Again, we can have a plot between the variables ln K and 1 by T. Ln K 1 by T. And we have a straight line with the negative slope. You can observe here minus EA by R. So this is the negative slope that we are getting there. So what is the slope value? Where the slope value is slope, which is m, minus EA by R. This is called the slope. Minus EA by R. And there will be an intercept here, which is ln A. We got a straight line with a negative slope, whose slope value is equal to minus EA by R. This is the slope value. This is the slope. From the slope itself, we can able to calculate the activation energy. Let us see how to calculate the activation energy with this slope. I'll explain. Okay, my dear students, taking normal logarithms, taking the exponential logarithms into normal logarithms, this can be 2.303 into log k is equal to 2.303 into log A minus EA by RT. Dividing with 2.303 from both sides to get log K is equal to log A minus EA by 2.303 RT. This is one more expression. When you plot a graph between log K and 1 by T here, log K and 1 by T, we have a straight line with a negative slope, whose slope value is equal to minus EA by 2.303 R, and intercept value is log A. Same graph only. Here we have used the exponential logarithms, here normal logarithms to the base 10. Whenever normal logarithm is there, the slope value will be like this, minus EA by 2.303 will be additive here. Okay, let us solve some numericals of the related. Please go through this. The activation energy of the reaction can be determined from the slope of which of the following graphs? Just now we discussed, that is nothing but ln K versus 1 by T. Just now we discussed. Ln K is one of the variable, it's nothing but the Y variable. 1 by T is the X variable. So we got the straight line with the negative slope, and whose slope value is nothing but minus EA by R. And intercept value is ln A. The slope of Arrhenius plot ln K versus 1 by T of the first order reaction is minus 5 into 10 power 3 Kelvin. The value of activation energy of the reaction is, and R value also given, which is 8.314 joule per Kelvin per mole. How can we calculate slope? We discussed this. Plot is drawn between ln K versus 1 by T, and what is the slope value? What is the expression of the slope? Minus EA by R. The expression of the slope is minus EA by R. So, minus, what's the slope is mentioned? Minus 5 into 10 power 3 is equal to activation energy we need to calculate here, minus EA by, what's the R value? It is given with the question itself, it is given 8.314. Minus will be cancelled. So activation energy will be 5 into 8.314 into 10 cube joule per mole per Kelvin. And this value is approximately 41.5 into 10 cube joules. But all options are given in kilojoules. So that 10 cube joules is 1 kilojoule. 41.5 kilojoules. Kilojoule per mole. One more question of the related, we'll see. The slope of Arrhenius plot ln K versus 1 by T of the first order reaction is minus 5 into 10 power 3 Kelvin. The value of the activation energy of the reaction is. Choose the correct option for your answer and given R value as the 8.314. Just now we discussed. So whenever ln K and 1 by T graph is there, What's the slope value? The slope value already told, we get that negative slope. So the negative slope value is minus EA by R. And that slope value also mentioned, which is minus 5 into 10 power 3 is equal to minus EA. We need to calculate activation energy here by our value 8.314. So minus minus is getting cancelled here. Activation energy is 5 into 8.314 into 10 cube joule per mole. And this value is 41.5 into 10 cube joule per mole, which is 41.5. 10 cube joules is 1 kilojoule per mole. Coming to the answer is 41.5 kilojoule per mole. Okay. Coming to one more question of the related. What is the activation energy for a reaction if its rate doubles when the temperature is raised from 20 degrees C to 35 degrees C? 20 degrees C to 35 degrees C. Dear students, we discussed this. What is an exponential form of the rate constant towards the activation energy? Ln K is equal to ln A minus EA by RT. Right? So, making it into normal form, 2.303 log K is equal to 2.303 log A minus EA by RT. Dividing with the 2.303 on both sides, we can have log K is equal to log A minus EA by 2.303 RT. Say at a given temperature, this is the rate constant K1. At T1 temperature, this is the rate constant K1. What I said? At T1, rate constant K1. I am writing one more rate constant at T2 temperature. Log K2 is equal to log A minus EA by 2.303 or T2. This is rate constant K2 at temperature T2. Say this is the expression 1. This is the expression 2. Why we had taken the two constants here? Because there in the question itself the two temperatures. So that we had taken two constants at two different temperatures. Right? Subtracting 1 from 2 we get. Subtracting 1 from 2 we get 2 minus 1. Then we can able to write log K2 minus log K1 is equal to, I am subtracting 1 from the 2. Log A will get cancelled. EA by 2.303 or 1 by T1 minus 1 by T2. And this can be log of log A minus log B expression, so that this will be log A by B. Log of K2 by K1 is equal to EA by 2.303 R of 1 by T1 minus 1 by T2. This is the expression that we should use to solve the above one. Substituting the values, we'll get that. Since it is mentioned rate doubles, K2 by K1 value become 2. Since it is given that rate doubles, K2 by K1 is the 2. Log 2 is equal to EA by, since we are asked to calculate activation energy in kilojoule per mole, we need to substitute R value in kilojoule per mole. 8.314 into 10 power minus 3. R value in kilojoules, 8.314 into 10 power minus 3 of 1 by T1. T1 in the sense 20 plus 273, which is 293 minus 1 by T2. T2 in the sense 35 plus 273, 308. Substituting these values, log 2 value 0.3010. So EA we need to calculate, and 2.303 into 8.314 That value is approximately 19.1 into 10 power minus 3. And here 308 minus 293, which is 15. Nothing but this difference, 15 by 293 into 308. Substituting all this, we'll get that activation energy in kilojoule per mole as 34.7, which is the answer. Coming to next question. An increase in the concentration of the reactants of a reaction leads to change in. Whenever concentration of the reactants increases, the number of the collisions taking place per unit volume increases. When concentration of the reactants increases, the number of the collisions taking place per unit volume increases. As a result of this, the collision frequency increases. As a result of collision frequency increases. So that an increase in the concentration of the reaction leads to increase in collision frequency. Increase in collision frequency. Coming to the next one. Given below are the two statements. This is a recent to 2023 NEET question only. One is labeled as assertion A and other is labeled as the reason R. Assertion A. A reaction can have zero activation energy. Reason. The minimum extra amount of energy absorbed by the reactant molecules so that their energy becomes equal to threshold value is called activation energy. Coming to the concept, my dear students, a reaction can have a zero activation energy is a wrong statement. Assume if zero activation energy in the sense every collision must be a fruitful collision. Every collision must be an activated collision, which is impossible. Which is impossible. Coming to the next one. This is assertion and reason time. This is a recent NEET question 2023. And coming to the assertion, a reaction can have a zero activation energy, which is not true, my dear students. A reaction cannot have a zero activation energy. If the reaction can have a zero activation energy, assume all the collisions must be an activated collisions, which is not possible. Every molecule must be an activated molecule, which is not possible for moderate reactions. And coming to that next one, the minimum extra amount of energy absorbed by the reactant molecules so that their energy becomes equal to the threshold value called activation energy. In the beginning itself, we discussed at the same point only. The minimum additional amount of energy like that we discussed. This is additional amount only. The minimum extra amount of energy absorbed by the reactant molecules to meet the threshold value called it as activation energy. So, assertion wrong, but reason true. A is false, but R is true. Coming to the next one. The rate constants K1 and K2 for two different reactions are 10 power 16 into e power minus 2000 by T and 10 power 15 into e power minus 1000 by T respectively. The temperature at which K1 is equal to K2 is. How to solve such kind of the questions, my dear students? From the given relation itself we can solve. What is the given relation? Given relation is K1 is equal to K2. Just equate their rate constants. What is the K1 is given? 10 power 16 e power minus 2000 by T is equal to K2. 10 power 15 e power minus 1000 by T. This 10 power 15 in 10 power 16 10 times and 10 is equal to, when you bring this e power minus 2000 by T to the opposite side, it will become e power, this minus 2000 by T become plus 2000 by T. E power plus 2000, still there is a minus 1000 by T. Did you get this? I brought e power minus 2000 by T to the other side so that it will become e power plus 2000 by T. And this will be retained minus 1000 by T. So e power 2000 minus 1000 by T. How much it is? E power plus 1000 by T. This is equal to 10. Taking logarithms on both sides, ln 10 is equal to ln e power 1000 by t, which can be ln 10 is equal to ln e power 1000 by t can be written as 1000 by t ln e to the base e. Ln e to the base e value become 1. Since ln e value is the 1, and this will be ln 10 is equal to 1000 by t. And coming into normal logarithms, taking into normal logarithms, 2.303 log 10 is equal to 1000 by t. From this, t is equal to log 10 to the base 10 value is the 1, 1000 by 2.303 Kelvin. Coming to the next one. Mechanism of a hypothetical reaction. x2 plus y2 gives 2xy is given below. x2 giving of x plus x, which is fast, x plus y2 xy plus y, which is slow, x plus y xy, which is also fast. But rate law can be written only for the slower ones. So which is the slower reaction here? The second one. So going to give the rate expression. Rate law or rate expression is a mathematical reaction. Rate is equal to rate constant K into molar concentration of the reactants, right? What are the reactants? X and Y2. Molar concentration of X into molar concentration of Y2. But one thing, my dear students, that you should observe that this is the reactant. If one of the reactants of the slower step may be the products of some other step, the kind of the reactants also we need to consider. That reactants also we need to consider. So that since the very first one is the fast one, for this we can able to write equilibrium reaction. Equilibrium reaction. For equilibrium reaction, we can able to write equilibrium constant. The first one assumed as the equilibrium reaction, so that I am going to give the equilibrium constant, which is equilibrium constant in terms of the concentration Kc. That can be written like this. Equilibrium constant, how to write? Molar concentration of the products by molar concentration of the reactants. Molar concentration of the products, x into x. That would become x square. Molar concentration of the products, x into x, x square by molar concentration of the reactants, x2. So from this, I am isolating x value. If x square value is Kc into x2, x concentration has become Kc to the power of 1 by 2 into, otherwise you can write root Kc into x2 to the power of 1 by 2. Take this expression as 1. Substituting 1 in the rate expression, then we can have, what is the rate expression that we had? Rate is equal to rate constant K into, in place of molar concentration of x, we can able to write what? Equilibrium constant to the power of 1 by 2 into x2 concentration to the power of 1 by 2 into y2 can be written as it is. No change with the y2. Did you understand this? Here I have isolated x concentration and I substituted x concentration here. So that this is the constant under root constant. When constant is multiplied with one more constant, it becomes constant. K into molar concentration of x2 to the power of 1 by 2 into molar concentration of y2. Coming to order of the reaction, overall order of the reaction. Overall order, how to calculate? Sum of the powers of the concentration terms. What is the power of x2? 1 by 2. What is the power of y2? 1. Which is 1.5 or 3 by 2. That is the overall order of the reaction. Coming to the next one. For a first order reaction, A gives products. Initial concentration of A is 0.1 molar, which becomes 0.001 molar after 5 minutes. Rate constant for the reaction in minute inverses. What is the first order rate constant expression? First order rate constant expression is K is equal to, this is the first order rate constant, 2.303 by T into log of initial concentration of the reactants to change in initial concentration of the reactants. Initial concentration of the reactants to change in initial concentration of the reactants. For first order, rate constant expression is 2.303 by T log of initial concentration of the reactants. Otherwise, this R naught can be written as A, initial concentration of the reactants. This RT can be written as A minus X for the change in the initial concentration of the reactants, where X is the concentration of the products formed at time T. What is X? Concentration of the products formed at time T. A minus X is the change in the initial concentration of the reactants. A is the initial concentration of the reactants. This is the initial concentration. This is the change in the initial concentration. Right. Coming to the question. K is equal to 2.303 by, what's the time here? The time is given in minutes. 5 minutes into log of initial concentration of the reactants is 0.1 molar by change in initial concentration of the reactants, 0.001 molar. And this will become 100 times. That is the log 100. Log 100 is nothing but log 10 square, like that you can write, which is 2. 2 into 2.303 by 5. And 2 by 5 value is the 0.4. 0.4 into 2.303. This is nothing but 0.9212. 0.9212 minute inverse. Answer is 0.9212 minute inverse. Coming to the next question. So the addition of the catalyst during a chemical reaction alters which of the following quantities? What is the catalyst? It is an external compound which is added to the reaction mixture and which alters the rate of the reaction by providing a different path of the reaction. So catalyst alters the activation energy. Such a way it alters the rate of the reaction. A positive catalyst lowers the activation energy. Such a way rate of the reaction increases. A negative catalyst increases the activation energy. Such a way rate of the reaction decreases. A catalyst alters the activation energy. So the right option is the activation energy. Coming to, in a zero order reaction, for every 10 degrees centigrade rise of temperature, the rate is doubled. If the temperature is increased from 10 degree to 100 degree, the rate of the reaction will become. So for zero order reaction, for every 10 degrees centigrade, the rate is doubled. So mu value is mentioned. Mu value is given as the 2. Since they have given rate is doubled, mu is 2. Temperature coefficient is mentioned 2. So temperature coefficient 2. What is the final temperature here? 100 minus, what is the initial temperature? 10. And when this rate will be doubled, for every 10 degrees centigrade rise in temperature, rate will be doubled. So that 2 power 90 by 10, 2 power 9, which is 512 times. 512 times. Coming to the next one. For a certain reaction, the rate is K into A square into B. When the initial concentration of A is tripled, keeping the concentration of B is constant, the initial rate would. My dear students, I am writing the rate expression. Rate is equal to K into molar concentration of A square into molar concentration of the B. And it is given that initial concentration of A is tripled, so that A become 3 times of the A. 3A whole square. And B can be taken as the constant, right? Which is nothing but 9 into 3 square is the 9, K into A square into B. So the final rate is nearly 9 times to that of initial rate. So it increases by a factor of 9. Coming to the next one. The correct difference between the first and second order reaction is that the rate of first order reaction doesn't depend on the reactant concentration. The rate of second order reaction depends on the reactant concentration. This is incorrect statement, my dear students. Why? Because only for the zero order, rate is independent of the concentration. For the remaining, rate depends on the concentration. Coming to the second statement, the half-life of the first order reaction doesn't depend on initial concentration of the reactants, which is true. The half-life of second order reaction does depends on A naught, which is also true. Why? Because we have the expression between half-life as well as initial concentration of the reactants as T half is inversely proportional to 1 by A naught to the power of n minus 1, where n denotes order of the reaction. N denotes order of the reaction. For first order, n is 1. So that when you place 1 here, nothing you will get here. So that for first order half-life independent of the initial concentration. The half-life of the second order depends on the initial concentration. That's also true. Except for the first order, for the remaining order, half-life depends on the initial concentration. For second order, in the sense what? T half inversely proportional to A naught, where n is 2 for the second order, 2 minus 1. So T half inversely proportional to A naught. For second order, half time is inversely proportional to initial concentration of the reactants. So second one is the right statement. Of course, no need to go through the remaining statements. Second one, when the initial concentration of the reactant is doubled, the half-life period of the zero order reaction is. Just now I had written the formula T half is inversely proportional to initial concentration of the reactants to the power of n minus 1. And for zero order, n is 0. For zero order, n becomes 0. Substituting 0 here, T half is inversely proportional to A naught to the power of minus 1. Therefore, we can able to write T half directly proportional to A naught, initial concentration of the reactants. Only for the zero order, T half directly proportional to initial concentration of the reactants. For zero order, of time directly proportional to initial concentration. When you go through the question, when initial concentration is doubled, half-life become doubled for zero order. Half-life become doubled for zero order. Coming to the next one, a first order reaction has specific reaction rate of 10 power minus 2 second inverse. Specific reaction rate is nothing but rate constant value. How much time will it take for 20 grams of the reactant to reduce to 5 grams? What's the expression of the first order rate constant expression? K is equal to rate constant 2.303 by T log to the base 10 initial concentration of the reactants R naught, change in the initial concentration of the reactants, RT. Right. So here rate constant value mentioned 10 power minus 2, 2.303 by, since they are asking the time, we need to calculate log to the base 10. Initial concentration of the reactants is 20 by change in initial concentration of the reactants, 5. That's nothing but log 4 value. Log 4 value 0.6020. Log 4 value 0.6020. Right? Then T becomes 2.303. This 10 power minus 2, when you bring the 10 power minus 2 opposite side, that will become 100 into, when it is multiplied with the 100, 60.20. And the answer is 138.6 seconds. Going to the next one. The rate of the first order reaction is 0.04 mole per second at 10 seconds and 0.03 mole per second at 20 seconds after initiation of the reaction. The half-life period of the reaction is. My dear students, here they have mentioned concentration of the reactant at a given time, T1. They also mentioned concentration of another reactant at a time T2. Asking about the half time. Let us calculate rate constant first. This is first order time interval formula. Since they have mentioned two concentrations at two time intervals, this is called first order time interval formula. According to this first order time interval, we can use K is equal to 2.303 by T2 minus T1 log to the base 10. Concentration of the reactant at time T1 by concentration of the reactant at time T2. So 2.303, what's the T2? T2 is 20 minus 10. 20 minus 10 log of what is the concentration of the reactant? R1 0.04 by 0.03. So that value will be 2.303 by 10. This is log 4 by 3. You can write log 4 minus log 3, where log 4 value is 0.6020. Log 3 value is 0.4771. Subtracting, we can get an approximate value of 2.303 by 10 into 0.125, an approximate value. But we are asking about the half-life period. How to get half-time period? T half is, for first order of time period is 0.693 by K. 0.693 by, and what is the K? This is the K. 2.303 by 10 into 0.125. And this 2.303 in 0.693, 0.3010 times. And 10 into 0.3010, 3.010. This is 1 by 8. So that in the numerator it will become 8. And its answer would be 24.4. That's about chemical kinetics, my dear students. Thank you. Thanks one and all.